Hello and welcome. In this video, we are going to talk about properties of radicals, how to use those properties to simplify radicals in a similar way that we simplified using exponent properties in the last video. We're going to talk about how to simplify with just numbers, how to simplify if there's variables involved. Then we're going to extend that into how do we add and subtract when we have values involving rational exponents or involving radicals. And we're going to wrap up by talking about how to write radical expressions in simplest form. And that's going to include when we need to rationalize the denominator. So let's go ahead and jump right in. So let's start with some basic properties that we can review that again come from the idea of the properties of rational exponents and how they might benefit us. So the product property says if we have two things being multiplied together inside under the same type of radical, so the 4th root or the 8th root, we could actually split that product into two separate pieces. Now, sometimes it's going to be helpful to look at these as two separate pieces, and sometimes it's going to be more helpful to look at them by actually multiplying the two numbers and combining that product. So what I mean by that is here we have the cube root of 4 times the cube root of 2. Well, I don't know what the cube root of 4 is, and I don't know what the cube root of 2 is. But if I multiply them, I get the cube root of 8. And I know that the cube root of 8 is 2 because 2 to the 3rd power is 8. The quotient property says basically the same thing. If we have the nth root of a over b is equal to, and this, I don't know if you would have noticed this, but this radical should stop right there, is equal to what I get if I separate those into two separate pieces. So if we split it into the nth root of a over the nth root of b. Sometimes it's helpful to be able to split those into two separate roots, and sometimes it's more helpful to look at them as one individual root. So for example here, the 4th root of 162 over the 4th root of 2, I don't know what the 4th root of 162 is, I don't know what the 4th root of 2 is, but I can take that expression and rewrite it as the 4th root of 162 divided by 2. Well, I know that 162 divided by 2 is 81, and that 3 to the 4th is 81, so the 4th root of 81 is 3. So we can use these properties to help us simplify radical expressions. Some things to remember and to keep in mind. Sometimes it's helpful for us to rewrite them in different forms or to use different properties to make our lives a little bit easier. Sometimes it's helpful to have one radical and then simplify. Sometimes it's easier to simplify and then create one radical. So let's look at these first two examples. The first thing I'm going to ask myself is, can I just simplify it in the way that it's currently written? The 5th root of 192, I'm not sure if that's an integer. I don't think so. The 5th root of 6, that's definitely not an integer. So because I can't simplify as is, I'm going to see if it makes my life easier to rewrite it like this. So let's figure out what 192 divided by 6 is. That's going to give me 32. So this is equal to the 5th root of 32, and we know that the 5th root of 32 is 2. When I look at number 3, I'm asking myself the cube root of 8 and the cube root of 64. If I can simplify as is, that's what I want to do. If I can't simplify it as is, then I want to combine 8 times 64. Well, I'm glad I don't have to combine 8 times 64 because that doesn't sound like my favorite thing to multiply here, but I know that the cube root of 8 is 2 and the cube root of 64 is 4, so this is going to equal 8 when I simplify it. So let's look at some more practice where we have to make that decision on how we want to adjust these problems. All right, so if you're feeling confident, I encourage you to pause the video and try and work through any of these problems that you can on your own. If you're not feeling confident, go ahead and watch me work through a couple of them and then try the remaining ones on your own. So when I look at number 1, the cube root of 12 is not an integer. The cube root of 18 is not an integer. So what I'm going to do is I'm going to rewrite this as the cube root of 12 times 18. But instead of actually multiplying 12 times 18, which I don't know what that is off the top of my head, what I'm going to do is I'm actually going to break it up into its factors. If I'm looking at cube roots, that means I'm looking for sets of 3 of the same number. So I know that 12 is 4 times 3, or that 12 is 2 times 2 times 3. And 18 is 2 times 9, or 2 times 3 times 3. So this is still 18, and this is still 12, but can I find sets of 3 now? Well, I have 1, 2, 3 2s, which means I can take a 2 out. And I have 1, 2, 3 3s, which means I can take a 3 out. And I have used every single value that's inside. So now I can just multiply 2 times 3 to get 6. So the cube root of 12 times the cube root of 18 is equivalent to 6. Now, if you didn't think about it in that way, you could also have multiplied 12 times 18 to get 216, and then you could have taken the cube root of 216 to get 6. So still, just like in the previous lesson, a couple of different ways we can go about doing this. For number 2, the first thing I'm going to ask myself is, can I take the 4th root of 80? Can I take the 4th root of 5? And I don't know that there's an even or that there's an integer value that does that. So my next thought is, what happens if I rewrite it as one expression? Well, then I get to take 80 divided by 5, and 80 divided by 5 is going to be 16. And the 4th root of 16 is going to be 2. And if you didn't know that the 4th root of 16 was 2, you can break it up into its factors. And that's how we get 2. So if you're feeling confident now, I'm going to encourage you to pause the video. Otherwise, keep going with me. Cube root of 4, cube root of 128, that's not going to be even values for me or integer values. So I'm going to rewrite this as the cube root of 4 times 128. And I could multiply 4 times 128, but that feels like math I don't really want to do. So I'm going to rewrite 4 as 2 times 2. And I actually know that 128 is 2 to the 7th. And if you didn't know that, you could just break it up into its factors. Half of 128 is going to be 64, and you could keep going. But 2 to the 7th, so 1, 2, 3, 4, 5, 6, 7. And I'm looking for sets of 3. So here's a set of 3, here's a set of 3, here's a set of 3. So I have 1 set of 3, 2 sets of 3, 3 sets of 3. So this is going to simplify to be 8. If you multiplied first, you could have gotten that this would be the cube root of 512, which is 8, which you could find by making a factor tree, or if you just knew that 8 to the 3rd power was 512, you could use that method as well. For number 4, there's no multiplication or division happening, so we just need to make a factor tree and see if the cube root of 135 simplifies at all. So I'm going to encourage you, pause the video, work through these last 3 problems on your own, and then unpause the video and see how you did. All right, hopefully you had time to work through this. 135 is going to be 5 times 27. 27 is 3 times 9, which is 3 times 3. Cube root, so I can take a 3 out. Don't forget your little 3 index on your radical. The cube root, what's left over is 5. So this doesn't simplify down to be an integer, but it does simplify. The radical simplifies to be something besides the cube root of 135. So the cube root of 135 is equivalent to 3 times the cube root of 5. For number 5, I'm going to rewrite this as one fraction with the radical around it, which means this is going to simplify to be the 5th root of 2. Now, I don't know what the 5th root of 2 is, but I know that that's more simplified than the 5th root of 16 over the 5th root of 8. Last but not least, I'm going to rewrite this as the 4th root of 100 over 4, which is going to become the 4th root of 25, which again doesn't simplify, but it is more simplified than it was when it was the 4th root of 100 over the 4th root of 4. What we're also going to learn later in this lesson is that you're not allowed to leave radicals in the denominator. You're going to have to rationalize them. So if you can simplify without that step, that's going to make your life a little bit easier. So let's look at this same concept, but let's add variables in and see how having variables changes, or really doesn't change that much, what we're going to be working with. All right, so if we're simplifying using variables, the same rules apply that applied before. And as a reminder, we can still expand things out when we're not sure what we're supposed to do. When in doubt, expand it out. So you're going to treat your variables in the same way you would treat your numbers. If I have a 4th root of x to the 4th over y to the 20th, I'm looking for 4 x's. Well, I'm not going to write out 20 y's, but this is the same thing. 1, 2, 3, 4. as the fourth root of 4x's, which is just going to give us x. On the bottom, we're looking at the fourth root of y to the 20th. So if I had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And I'm looking for sets of 4. I'm going to have 5 sets of 4. So this is going to become x over y to the 5th. You could also rewrite it using rational exponents. So this would become x to the 4 over 4 over y to the 20 over 4, which again will get you back here. Now for part D here, 27, the cube root of 27, well 27 is 3 times 3 times 3. So that's going to give us 3. D to the 12th, how many sets of 3 do we have? We have 4 sets of 3. And again, if you're not sure, expand it out. 3, 6, 9, 12. We have 4 sets of those D's. So I'm going to encourage you, if you're feeling confident, go ahead and pause the video and work on numbers 7 through 10 on your own, and then unpause the video and see how you did. So for number 7, the fourth root of 64 is 4. This is the same thing for y as y to the power of 6 over 3, which is y squared. Or you could write out 6y's and figure out how many sets you have. Here on number 8, this is the same thing as x to the power of 4 over 4, y to the power of 8 over 4, which is going to become x over y to the 2nd. For number 9, I'm going to deal with each piece individually. So the 5th root of 4, that's not going to simplify at all. We have 8 a's, and we're looking for sets of 5. So I can take 1 set out, and I have 3 remaining on the inside. Then I'm going to look at B. I have 14 B's, and I'm looking for sets of 5. So I have 10, 20, I need one more. So I have 2 sets that can come out, so B squared is going to come out, and then I have 4 left inside. For C, I have 5 of them, so the C is just going to come out and there won't be any C left over. So our final answer, our simplification, is going to be AB squared C times the 5th root of A of 4 times A to the 3rd, B to the 4th. And then for number 10, let's clear some space first. Let's deal with the numbers first. 14 divided by 2 is 7. Then we can look at our x's. I have x in the numerator, so that's x to the 1st, minus the exponent in the denominator using properties of exponents. Y to the 1/3. There is no y in the denominator. There is no z in the numerator, so I'm going to call that z to the power of 0 minus the denominator's exponent for z, which is -6. So here I'm using properties of exponents. So let's go ahead and simplify. This is going to give us 7x to the 1/4. 1 minus 3/4 is 1/4 times y to the 1/3. Z to the power of 0 minus -6 is going to become z to the power of 6. And this is my simplified expression. One thing I want to point out is if the problem starts with radicals, your final answer should have radicals if we're making a decision between radicals and rational exponents. On number 10, our initial problem started with rational exponents, so our answer has rational exponents. On number 9, our original problem was in terms of radicals, so our final answer is still in terms of radicals. Now that we know how to simplify, let's talk about how and when we can add and subtract with radicals and rational exponents. I want to make sure we're on the same page with vocabulary, and I know I've been using some of these words throughout these lessons as well, but I just wanted to give you a nice visual of the different parts of a radical. So first of all, the number inside the radical is called the radicand. The radical symbol itself is called a radical. The number that's here is called the index. If there's no number written there, that means it's a square root, which means it's implied to be 2. And if there is a larger number out front, that's called a coefficient, just like it is with 5x. So remember, if you're writing an expression, you need to make sure your index is small and on the inside of this little radical tail to make sure that it's clear that this isn't 3 times the square root of 7, it's the cube root of 7. So remember, if the index isn't shown, it's implied to be 2. Just like with variables, like terms or like radicals mean they have the same index, that's this number, and the same radicand, that's this number. If we have like radicals, then we can combine them in the same way that we combine like terms. So we can add or subtract. If the radicands are not the same, or if the index is not the same, we can't simplify them with addition or subtraction. So what we're going to try and do is manipulate anything we can to get like radicands. So back with normal numbers, if we had something like 2x plus 5x, we could combine that to be 7x. We could not combine 2x and x squared because they aren't like terms. So the same properties are going to hold true here. If you look at example E, we have 8 to the power of 1/5 and 8 to the power of 1/5, which is the same thing as the 5th root of 8, which means we can combine them. Just like when we combined x's here, our 8 to the power of 1/5 isn't going to change because what we're really doing is saying how many of those 8 to the 1/5 do we have? We have 2 plus 10 more. So we have 10, 12 times 8 to the power of 1/5. And we're not going to simplify this any further. For part F, we have cube roots, so our indexes are the same, but we have the cube root of 54 and the cube root of 2. Those aren't the same. So what we need to do is we can't do anything unless they are the same number inside. So let's go ahead and make a factor tree or make an upside down birthday cake with 54. Well, we can rewrite the cube root of 54 as 3 times the cube root of 2 minus the cube root of 2 that was already there. So now we have like radicands and like indexes. So we can say 3 minus 1, which is going to be 2, times the cube root of 2. Again, notice on example E, the original problem had exponents. On example F, the original problem had radicals. So our final answer should match that same notation. Let's look at a few examples that use these properties, and then we will move on to our last topic of this video. All right, I'm going to encourage you, pause the video, work through any of these problems that you can on your own, and then unpause the video and see how you did. All right, hopefully you had time to do that. On number 11, we already have like radicals. So this is really just saying what's 1 plus 7. There are 8 what's? There are 8 of our 4th root of 10. On number 12, we already have like radicals. So we have 6 minus 2. So there are 4 what? 4 of the cube root of x. On number 13, we have like exponents. So what do we have? We have 5 of these and 6 of these. So we have 11 of our 7 to the power of 1/3. On 14, again, we have root y and root y. So we have 5 root y's and 6 more gives us 11 of those square root of y's. 15 and 16 is where we start getting a little bit more challenging because the bases or the inside of the radicals, the radicands, are not the same. Well, we already simplified the square root of 54 back on example F. So I'm going to rewrite 12 times the cube root of 2z to the 5th minus, and we're going to simplify this. So 54, we said, simplifies to be 3 times the cube root of 2. So there was already a z there. So I'm going to take a 3 from that 54, and I'm going to leave a cube root of 2 here. And we still don't have identical radicands. So we need to deal with this part. Z to the 5th, if I'm breaking it into 3's, that means I'm going to have 12. I can take one set of 3 out. That's going to leave me with 2z squared minus 3z times the cube root of 2z squared. Now we have like radicands. 12z minus 3z is going to be 9z times the cube root of 2z squared. And last but not least, 48, we're going to be able to simplify to be 2 times the 4th root of 3 minus 1 4th root of 3. So we have like radicands and indexes. So this is going to be 2 minus 1, which is just 1 times the 4th root of 3. So hopefully you're starting to feel confident in this. We're going to talk about one last thing, which is making sure we have our final answers written in simplest form, and what happens if we have a radical in the denominator. Okay, so we're going to talk about writing radicals in simplest form, and we've already been doing this, but just to make sure that your final answer is as simple as possible, make sure all of these following things are true. So first of all, that there's no more nth powers that can be factored out, that there are no fractions inside the radicands, or there's no fractions inside the radical, and that no radicals appear in the denominator. And that's sort of the new one here that we need to make sure we're talking about. In order to meet that last condition, occasionally what we're going to need to do is called rationalizing the denominator. And what that means is we're going to multiply the numerator and the denominator by an appropriate form of 1 that allows us to simplify that denominator to be a number that no longer has radicals. Sometimes that's going to involve using conjugates, just like we did when we were dealing with quadratics, and sometimes that's going to involve simplifying to see what needs to be multiplied by to get that radical out of the denominator. So let's look at these last 4 examples together. So for number 17, the first thing I notice is I can simplify that numerator. The 4th root of x to the 4th is going to just be x. But the denominator, the 4th root of 2y cubed, that denominator isn't going to simplify. So what I'm going to ask myself is, what do I need in order to be able to take the 4th root? Since the index is a 4, I'm actually going to go ahead and rewrite this down here, 4th root of 2y cubed. Since the index is a 4, I need sets of 4s. What that means is I need 3 more 2s because I only have 1 right now, and I need 3 more 2s inside my 4th root, and I need 1 more y because right now I already have 3 and I only need 1 more to make 4. So I'm going to multiply this in both the numerator and the denominator. When I do that, in the numerator, I'm still going to have that x that was already there, and now I'm going to be multiplying that x by the 4th root of 2 times 2 times 2 is 8y over, I now have 1, 2, 3, 4 2's, which means I can take a 2 out. And I have 1 plus 3, 4 y's, which means I can take a y out. So this is going to simplify to be x times the 4th root of 8y over 2y. Now for number 18, if we look at that, the issue is that we're not allowed to have a square root in the denominator. In order to get rid of that, just like we did when we were learning about conjugates, we're actually going to multiply both the numerator and the denominator by the conjugate, which is going to be x minus the square root of 3. When we do that, remember our denominator is going to give us the difference of squares, which is going to make it easier to multiply, right? If I have x minus 2 times x plus 2, when I multiply that, I just get x squared minus 4. I just multiply the first 2 and the last 2 because the middle 2 are going to add to be 0. So I'm going to look at the denominator here. When I multiply x plus root 3 times x minus root 3, I'm going to multiply the x's to get x squared. It's going to be subtraction because I'm multiplying a positive by a negative. Root 3 times root 3 is the square root of 9, which is 3. So the denominator is going to become x squared minus 3. And the most important thing there is that the denominator no longer has a radical in it. The numerator, if I multiply 1 times x minus the square root of 3, I just get x minus root 3. So now I have x minus root 3 over x squared minus 3. All right, I'm going to encourage you to pause the video and work through 19 and 20 on your own, and then unpause the video and see how you did. All right, hopefully you had time to work through this. On number 9, the 5th root of 7, on number 19, the 5th root of 7 doesn't simplify. I'm going to rewrite this down here, 5th root of 7. But the problem is we can't leave the 5th root of 8 in the denominator, so I need to get rid of it. So let's think about what 8 is. 8 is 2 times 2 times 2. If I have a 5th root, I need to have 5 2's. So how many more 2's do I need? I need 2 more 2's. So I'm going to multiply by the 5th root of 2 times 2 over the 5th root of 2 times 2. My goal in doing this is that now I have 1, 2, 3, 4, 5 2's, which means I can take the 5th root of that denominator and just get 2 in the denominator. So I no longer have a radical in the denominator of my problem. Now, in the numerator, since I'm multiplying and these have the same outside index number, I can multiply 7 times 2 times 2 or 7 times 4. That's going to give me the 5th root of 28. And that's not going to simplify at all because I'm not going to have 5 of any number that's the same. All right, last but not least, number 20, we're going to multiply by the conjugate. It's okay that there's no x here. The conjugate is still exactly what I see, but opposite in sign. So the square root of 7 plus 2. That means my numerator is going to become the square root of 7 plus 2, since it's just that times 1. My denominator is going to be the square root of 7 times the square root of 7, which is 7, minus 2 times 2, which is 4. So this is going to become the square root of 7 plus 2 over 3. No radicals in the denominator. That's how I know I'm all the way simplified. So let's go ahead and talk about what we learned in this lesson. We reviewed different properties involving radicals, and we talked about how sometimes it's helpful to multiply or divide and then take the nth root, and sometimes it's helpful to take the nth root and then multiply or divide. So we have to pay attention to the way the problem is written and how it's going to be easiest for us to work with. We'll get better with that as we practice more. So we simplified radicals both with variables and with numbers and with a variety of different indexes. We then talked about the different parts of a radical and how we can add and subtract like radicals when we have the same radicand and the same index, and how to manipulate a radical to try and get that index and radicand to be the same. Lastly, we talked about writing radicals in simplest form, and we focused specifically on how do we rationalize the denominator to make sure that we don't have any radicals in the denominators of our final answer. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.